Welcome back to your Algebra 1 Semester 1 final review. We're looking at problem 41, or whatever number it might be for this year. Regardless though, you should see a problem that has two different inequalities. We call this a system of inequalities, and you'll see two equations that look pretty similar on each one. You've got what I'm going to do in orange here, and then you have a purple one. Now, because they're all fairly similar, we should at least try to eliminate options that don't match our graph. And I think the easiest one to eliminate first are the ones in orange, because all of the orange equations are in that y equals mx plus b form. Now I put an equal sign here. There's no equal sign in the problem. The only thing that changes though is if your line's going to be dashed or solid, but this equation for all of them is still going to be the equation of the boundary line. It's going to be the line that separates the shaded region from the non-shaded region. So we still should be able to use these even without an equal sign to get an idea which dashed line over here is the right dashed line. So you'll notice for the first one, there's a y-intercept of -1 and a slope of 1/3. Let's see if that matches the graph. If I start at -1 and then positive slope up 1 over 1, 2, 3, up 1 over 1, 2, 3, I think that graph doesn't actually match any of the ones on our doesn't match any of the lines on here. So I think any of the ones that say 1/3 x minus 1 are going to be out. 1/3 x minus 1, 1/3 x minus 1. Cool. So then we check the next one just to make sure. So this one says start at a y-intercept of -1 and now use a negative slope of down 1 over 3. So if I start at a y-intercept of -1 and go down 1 to the right 3, you'll notice that all these points end up on this boundary line, this line that's separating the shading from the non-shading. So this equation right here, and I'm going to label it just so I can really keep track, is that y, and then I'll do equals for now, 1/3 x minus 1. Oops, don't forget the negative slope. That must mean then that this other line has to match the other equation. Now we could do the same thing, but you'll notice that the only options left are B and C have the same equation, so I'm fairly confident then that this one has to be the other one. Now you could do our same trick from before and verify, and you probably should, that this boundary line matches this equation, but I'm not going to take the time for it now. Instead, we need to get to how we decide between is the answer B or is the answer C. And you'll notice that the only differences at this point, I'm going to erase the highlighting to see here, the only differences are which way the equality signs are facing. And it's the same thing for the second one, which way the signs are facing. The first one we have y less than, and the purple equation has a greater than, and then vice versa for part C. So how do we decide what goes where? Well, there might be a couple tricks, but really the foolproof way is to pick an answer that should work and plug it into each equation to make sure that the answer works in the equations. So how do we know what answers work? Well, that's the whole point of shading a graph. The shading on a graph shows us any point that works. And in fact, if you look at the shading up here, there's lots of different points up here that work. Okay. Now, my favorite point to choose is the point 0, 0, and I would suggest that you probably try 0, 0, but for the sake of this example, I'm going to choose a point that has a different x from a y just so we can see the difference. So I'm going to choose the point 1, 3. And what I'm going to do at this point, and I'll start with b over here, I'm going to make sure that this point 1, 3 works in each equation. So, checking answer choice B. I have two equations to check. The first one is the equation y is less than -1/3 x minus 1, and the point that I want to use again is the point 1, 3. Don't forget that points go x, y, so that means in my equation here I have a few things that won't change and a few things that will. The x needs to be replaced with a 1, and the y, of course, needs to be replaced with a 3. Let's do a little math here. This is saying, is 3 going to be less than, we have to do a little multiplication, -1/3 times 1 is -1/3. And then this subtraction isn't bad. If you're at -1 and you subtract a third, now you're at -1 and 1/3. They're saying, is 3 smaller than a negative number? And you should all be saying, no, 3 can't be smaller than a negative. So I tried 1 comma 3, and when I simplified everything down, I got a statement that was false. It says 3 is less than a negative. That's not true. But this point is in the shaded area, which means we should have gotten an answer that was true. And because this gave us something that's false, we know the equation didn't work and it can't be b. Now, that only leaves one equation left, so we're pretty confident that will work. But why don't I try 1 comma 3 in this other equation just so we can see the difference. So the other equation was, now we're going to do c over here, 2x minus 4y is less than 8, and I'm going to try the same point, 1 comma 3. It's in the shaded region, it should work. So we need to replace the x with 1 and the y with 3. So let's take a look. X is 1, y is 3. We end up with 2 minus 12 is less than 8. And that gives us negative 10 is less than 8. Is that true? Oh, I think it is. Yeah, negatives are smaller than positives. And that shouldn't surprise us because C is the only one that's left, so it better work. So again, the first thing you want to do is narrow down which lines are on there, and that was able to eliminate 2 equations for us. And then the second step is pick a point that's in the shaded region and start trying that point in really every equation. The right answer will be the one whose point works in each equation.